Great. Thank you so much, Lane and Eli, for inviting me and everyone who is here. It looks like a lot of people, so I welcome you and hopefully you get something out of this talk. I'm going to talk about 15 years, and I actually think this is year 17 because I planted our first iteration of this project when I was pregnant with my now almost 17-year-old son. And so this has been an ongoing part of my work here in Minnesota, and wanted to share kind of a summary and some thoughts on what we have learned from this work. In that 17 plus years, I have not done this alone by any means. I have worked very closely with a number of people, including Peter Reich, Artur Stefanski, who's at University of Wisconsin-Stevens Point, and Rai Bermudez, who's our long-term project manager. The project also started with a number of other people, and we could never have done this without the many, many interns who have been our on-the-ground staff since the project started. Graduate students, postdocs, visiting scientists, folks from the Forestry Center have all played a big role. So I just want to shout out to everybody, even though I'm presenting this work. It is by no means just my own work. It's a collaborative and collaborative effort. So where are we? I like to start with place. Where are we? We are in the center of the continent, the middle of Turtle Island, North America. We are at a place where different vegetation types come together. On this kind of map of biomes, we see the prairie, which looks yellow to me in this in this graphic. The temperate forest to the east, that looks kind of a light green to me, and the boreal forest in the north. So we are a place of intersections of vegetation types. We are also a place of intersection of nations and people, and a place where people come together and interact with this intersection of vegetation and shape that vegetation. We are at a place, and I love this picture of from the North Shore, really showing that we're at a place of ecological mixture, of cultural mixture. You see species in this photo like the sugar maple that here in Minnesota is close to its northern range limit, and this tree species lives as far south as Georgia. You also see in here aspen, which you will find all the way to the Arctic tree line. You see species in here who part of their life history is intimately tied with fire. And this mixture here is really a result of interactions of the biology of the species, the environment, and the people who have tended and continue to tend these forests. A key concern for me, and I think maybe many of you, is what happens as the climate changes? What happens as we get warmer here? What happens to the interactions that have shaped these forests in the regions? These interactions that are really predicated on a climate that is changing and will continue to change in the future. There's uncertainty. I ask myself often, what does the future look like in this region? What if the future is invasive, not non-native species that don't know how to behave in this region? What if the future is wet? Many of the trends show a wetting trend in this area. How do we manage if the future is wet? How do we interact with the forest? What if the future is dry? Even though we see wetting trends, we also are seeing more periodic drought. The heat is pulling and demanding more of that water. So I think there's a lot of questions, and we are really in a place where we are asked to manage, steward ecosystems sustainably now and into the future. And we're doing this for climate change, right? For adapting our interactions with the forest in the light of climate change. But this isn't something in the future. This is happening now. So we are also working with it. We're not going to turn the clock back. We are in a space where the climate is changing and we have to adapt our interactions uh, to deal with this. How do we do this? I think this is a lot of the questions people are asking. How do we do this? What do we know that can be applied to this? And so I'm hoping today what I show you helps thinking about how trees respond to a changing climate, and that better understanding how those trees may interact with some of the drivers that can help us plan, make decisions, and steward these lands into the future. So today, as I said, I'm going to share lessons that we have learned from, it's now about 17 years of warming and about 13 or 14 years of reduced rainfall at what we have called the B4WarmED experiment, boreal forest warming at an ecotone in danger. And when this project started, it was just about warming. And as you will see from the presentation, it became very clear that water was obviously important and that warming and alterations of water go hand in hand. And so we added an experimental framework that looked at water. So back to place, where is this work conducted? We have two sites in what we call Minnesota. The Hubachek Wilderness Research Center. This is near Ely, Minnesota, and is on lands that were ceded in the 1854 Treaty of La Pointe, so within the 1854 Treaty Authority. The second site is the Cloquet Forestry Center. So this is about closer to that transition from the hardwoods into boreal forest. And this is on unceded lands of the Fond du Lac Band of Lake Superior, Chippewa. And these are lands that we are working actively to return, as well as co-steward with the Fond du Lac Band. This is a super, super ecologically interesting region, I think. It's a place where, as I said, vegetation types and people and species of trees come together and overlap. So we have a suite of species that are really more northern, right? They are at their southern range limit here in the region, and they go way up north into much colder regions than here. And then we have a bunch of species that are alternatively, this is their northernmost region, right? They are near where maybe they have some cold limits and occur some not so far south, like cedar or Thuya occidentalis, but others like red oak, Quercus rubra, or Acer rubrin, occurring all the way down into Georgia and Florida, so much warmer places. This is also a place that we have brought species. And these species, like Frangula alnus and Rhamnus cathartica, both from Europe and Eurasia, have been brought here and don't know how to interact with our species. They don't have a history with this place or the species And they are ill-behaved, as we all know. Their populations are growing. They are creating problems for our local species here. And so this is a place where we have this mixture, and all of these are part of thinking about where these forests are going to go in the future. So in this work, we had some pretty simple hypotheses or expectations. The first one was just that species at their warm edge of the range might do poorly, right? If they are near kind of their heat limits, giving them more heat might not be a positive thing. And I think when we think about climate change, we often think about this doom and gloom. It's that everything's going to do poorly, or the world is falling scenarios. But there's some species that actually might be like, oh, I've been so cold. It's so nice to have it warmer, right? So there's these species who are at their cooler edge of their range, and maybe those species will thrive. And some of the climate envelope modeling supports this and suggests this, and we're starting to see some of this on the ground. So when we started this project, these were kind of our basic, simple hypotheses of real species differences in how they respond to warming. So what did we do? Tried to kind of put a whole bunch of things on this slide to just lay out the project as a whole. First off, we had a whole bunch of 3-meter or 9-foot diameter plots. And I'm going to get my little pointer out here because this helps. This is one of our plots, and you can see this whole range of different colors, and in each of these slots, a tree is planted. So we plant juvenile trees. At this point, we have planted upwards of 20 different tree species, as well as some non-native shrub species and some new species this year that I'll talk about later. Into these plots, we have 72 of these. They are set up in a design where some of them are under canopy, some of them are in the open, with this idea that trees in this region regenerate, and their juveniles grow and maybe have preferences for growing in the open or growing in the shade. So we really wanted to test warming in both of these key environments for tree regeneration. We have 3 different warming treatments: an ambient, where we aren't manipulating, one that we increase by 1.7 degrees Celsius, or about 3 or 4 degrees Fahrenheit, and another one that we increase by about 3 to 3.5 degrees Celsius. So this is more like 5 to 7 degrees Fahrenheit. So those 3 heat treatments, and then crossed only in our open sites, we have rain exclosures. You'll see more of this, so you don't have to, don't worry about remembering all these details. We heat using infrared heating, above ground, and resistance cables, like the kind that you put on your roof to get rid of ice dams. Below ground, we heat only in the summer. So not in the summer, I shouldn't say that. We heat from snow off to snowfall for the most part. So about 200, 220 days of the year. And in the summer, we exclude rainfall on an event by event basis by rolling out these tarps. Someone runs out, opens a tarp, and then we keep track of how much rainfall. And the goal is about 40% of summer rainfall excluded. Let's see, some close-ups here. I love this picture. You can see the heat lamps here. But this picture is really to cue me that we planted our juvenile trees into a mix of existing vegetation. So you can see, you probably can't see the individual trees here because they are planted in a mix of other vegetation. Here's a little close-up of these ceramic heaters. The cables are buried about 10 centimeters below ground, and we heat on a feedback control system, which means that we see what's the temperature in ambient, and then we put enough heat into our warmed plots to bump it up by the amount that we want to augment the temperature. So it cycles. When it's cooler, you know, these warm plots are cooler, but they're always that differential above what the ambient is. We've studied a lot of things. Phenology, soil processes, mycorrhizae, endophytic fungi, plant-insect interactions, seed germination, plant secondary chemistry, the ground layer vegetation and its phenology, physiology and growth. I am going to highlight a number of these different topics, but not go into a ton of depth uh, on any of them, focusing probably most of the depth on the growth and survival data, because I think that's kind of the most applicable, and the rest of it helps us understand maybe what the underlying processes that are going on that might be leading to those growth and survival outcomes. So, with no further ado, I'm just going to jump right in. Lessons learned. One of the lessons we've learned is, and we're seeing this, I think, in a lot of places and just in our daily personal observations, is that all of our species extended their leaf-on period. They leafed out early in warmed plots. They dropped their leaves later. The drying treatments didn't alter this a ton. But one of the things that's interesting is that for some of these species, even though they had this longer growing season, and in some cases, this longer growing season was 9 to 17 days on average. So that's almost 3 weeks longer. And in sugar maple's case, actually, on our longest year, and there's variation from year. I think our sugar maples had their leaves on for a month longer, right? But for some species, even though they had these phenological responses, it didn't translate into growth. And some of that might be that when you leaf early, you have the potential for frost damage. So we're pushing some of these envelopes in terms of risk. If you hold your leaves late, you also have the potential for frost damage and not pulling those nutrients back into the leaf before that leaf drops. And I just wanted to take a minute to show some data. I'm going to show some data slides here. I love data. I know not everyone loves data and not everyone loves data graphics. So hopefully I can walk everyone through these, and you too will appreciate maybe data if you don't come to love it. All right, so let's get my highlighter again. So on this graph, we have day of the year, with 0 being January 1st. So 90 days is like the beginning of March. And we did shoot length phenology, which I think this is a really unique data set. A lot of people look at leafing phenology, which we did too, but we also measured that shoot development through time, through the growing season. And we see some really different responses. One of the things we see is this almost everyone thing leafs out early. So this is shoot length. This is, these dots are when they started growing, more or less. And then this is when they stop. So we can see like how long did they grow? How much did they grow? And we can see the species have different patterns, right? Everything seems to start a little bit earlier. But they don't all put on a lot of new growth. So oaks, well, we see actually increased biomass. Their shoot lengths aren't actually growing a lot more in the warming compared to maple here, where you see that this red line, at least it looks red to me, is our warm treatment. It starts earlier and grows more. Buckthorn, Rhamnus cathartica. We maybe don't want to see this, but buckthorn loves the heat. It starts growing sooner, it grows faster, and it grows more. And red pine, Pinus resinosa, well, it starts earlier, it stops earlier. So overall, that phenology isn't leading to greater growth. Okay. Uh, Forest tent caterpillars, number two. This is just a little bit of a teaser. I feel like we did a small project looking at these interactions early on in the project. You can see this is from over 10 years ago, but it was pretty interesting, and I would love if anyone had interest in this to see more of this type of work. So we found that forest tent caterpillars were actually more synchronous with aspen and birch leafing with warming. Um, and so here's another graphic. This is the time between when eggs hatched and buds broke. So generally, these forest tent caterpillars hatched before bud break and just hung out and waited until the buds broke. And you see our ambient treatment and our two warming treatments. And what you see, especially I would say in aspen, is that in the ambient, the forest tent caterpillars come out earlier. This is aspen, this is birch. And then they sit around, and this is a time where they might get hungry, they might get eaten by a bird, they might get parasitized by a wasp before they're able to feed on the foliage. In the warming, that period of risk is shorter. And this is 2 different years. So in this year, it was shorter for both. And this year, aspen kind of became more synchronous. What does this mean? In my mind, it suggests perhaps that this synchrony could increase potential for damage. It's a teaser, right? It's one of those results that you're like, oh, let's learn more. Because these forest pests and diseases are one of the things that we are really watching out for in this changing climate. Number three, we had some work looking at anti-herbivore compounds in some of our species, especially species that are that might be or important browse for various of our wildlife species. And for I'm just showing 2 different compounds here. We see a reduction in those compounds in the warm temperature relative to the ambient. And again, this is suggesting climate change altering chemistry. This might be have an implication in terms of reducing some of the, increasing palatability. We would need to couple nutritional quality with these to really see, and I think that would be a fun direction to be delving a little bit more into how is the browse quality changing over time. Buckthorn, everybody's favorite plant to dislike. I think in northern Minnesota, buckthorn is maybe not as big of an issue as in southern Minnesota, where it can form really dense thickets like this. And the bad news, very bad news from our project is that, wow, with warming, buckthorn had enhanced germination. It had higher photosynthetic rates. It had faster growth. It had earlier and longer phenology that you saw translated into more growth. It had higher survival. Um, so all of these things really point to a species that is poised to thrive in the future conditions here. And I think that is something to keep in mind. that buckthorn management and its impacts may become a larger part of managers' portfolio in the future, especially in areas where it's not already a big part of the portfolio, and this comes then at the detriment to other activities. Okay, here's what everyone's waiting for, right? The growth data. The take home is not great. We across the board really found that boreal forest tree species grow less with warming, and temperate species grow more. Um, this change is pretty significant. I mean, overall, I'm just highlighting a few of the species here. And again, this is early results that have been kind of upheld, is that there are a number of species that really grow significantly less, is juveniles from 20 to 40% less, or 20 to 40% more. And I think I have a graph here. Yeah. This graph is really showing percent change in diameter. So this is just one part of growth. Doesn't look quite as stark. And this is just over a few years, but you can see now breaking out for a number of our species in the region, these reductions in diameter compared to ambient. So smaller diameter compared to ambient in some of these, key species like white pine and white spruce. Aspen doesn't seem to be super affected, nor does paper birch to simply warming. And here's that buckthorn. Happy buckthorn. And many of these results come from differential effects of water. And so I'm going to want to talk about water for a little bit. One of the things that we found is that water was pretty key to some of these responses, and especially to some of the negative responses. So when it was warm and wet, all of the species grew more, right? So if they're given more warmth, even those northern species, and they have enough water, they're going to grow more. That enhancement is much greater in species like maples and oaks, the more temperate species, than the boreal species. But if it's hot and dry, they all do poorly, right? They all have lower photosynthetic rates that can translate into lower growth rates. But the negative effect of those hot, dry periods is much larger, especially for those boreal conifers. And so it's really thinking about, again, going back to how I started, like, what if the future's wet? What if the future's dry? That's really kind of a critical piece of this. The future is going to be warmer, but is it warmer and wetter, warmer and drier? I would say that warmer and drier is going to have the kind of most drastic impacts moving forward in terms of the potential to shift composition. I'm going to get to that in a couple more slides. Let's see. Here's some data. I love data. I hope you're not. I hope everyone's still with me and not minding my data slides. That this graphic is bar graphs looking from our ambient across these two different warming treatments. And we're looking at survival and stem biomass. And we have our ambient rainfall and reduced rainfall. And so this is white spruce. And we see generally white spruce has reduced survival in the warm treatments, and that this is particularly pronounced. Like it seems okay if it's a little bit warmer, but then if it's a little bit warmer and drier, we get this reduction in survival. And this isn't insignificant. 40% survival rates compared to 80%. This is cutting survival in half. And then associated with that, we see these changes in stem biomass. And then we see even in spruce, even though it has 80% similar survival, those surviving trees in the drier sites are smaller. So I'm going on, and people might be saying, oh, but these are just small trees, right? These are juveniles, they die a lot. But I would argue this is the future of the forest. In order to get those canopy trees, you must have juveniles, and you must have juveniles surviving and growing in order to reach that state. And when you start getting these drastic reductions in survival, your pool is much smaller for that future canopy. Sugar maple, really different responses. Here we are, these temperate species. The treatments are less evident in survival, right? They seem to have high survival across the treatments. Even sugar maple in the dry maintain pretty high survival. And we see again this enhancement of growth where stem biomass is, doubled, if not more, in the warming treatments, and that we even see that enhancement in the warm and dry. So this really highlights this potential for transition of this region from these more boreal species towards the more temperate species. This is that future regeneration layer, right? This is potentially some of the patterns that are going to play out there in the future. And so if we want to keep some of these species in the mix, we are going to need to put in some additional care and stewardship. Let me see. Why poor juvenile tree growth? Some of it has to do with reduced photosynthesis. Some of it actually has to do with below ground and below ground impacts. And one of the things that we have seen, and this graph is just showing you that kind of negative growth of the spruce. One of the things we've seen looking at mycorrhizae, so these are those fungi that associate with roots that support the tree in terms of taking up nutrients, taking up water, and also connect trees and allow for resource sharing, which in some cases can be supportive and in other cases can be draining. And what we've found is that in these dry treatments where we have warm and dry and we have trees with poor juvenile growth, most of these trees that have this poor growth also have reductions in their mycorrhizae and their mycorrhizal networks. And so reduction in that really important interaction, interconnection with a fungal partner that supports that growth. And so that's for those of you who are curious, like I am, about the why, the mechanisms underlying some of these growth differences. That's one of the things that we've been learning, that both these mycorrhizal networks as well as the physiological shifts are really some of the underpinning of those results. So this is my last data slide. And this is there's a lot on this. And this is, I'm gonna actually put my teacher hat on a little bit here and get out a drawing tool to help unpack this because I think there's some interesting patterns to really see in here. I've been told like never use a pie graph, but I think a pie graph in this case is very useful. So what this is we took a look at the those community level results related to the survival. And so each of this pie relates to the proportional abundance of each of the species within each of the treatments. So we see that we have treatments across the top here and warming treatments across the top, rainfall treatments along the side, and then each pie graph with a different color or pie size is a different species. And I just want to walk through a couple of these because I think it's telling. So first off, I want to highlight the maples, right? And it's, if you just look at the maples, right? If you say that's about their pie size in ambient, and then we warm them and look at their proportional abundance. Quite a large increase in both of these warmings. I think highlighting these two, you can see that pretty well. Well, in contrast, here's our spruce and fir, our typical boreal. And look at that. They just become less and less abundant in these seedling pools. So this is taking not just the growth and survival, but putting it into this regeneration layer, community context. And we see this shifting composition within that. For those of you who birch is an important species, and certainly it's a culturally important species in the region, one that there's been some concern about. In our ambient rainfall, the birch, holds its own and does quite well. But once we get into reduced rainfall and hot, so hot and dry, we see birch, and I'm just going to highlight the birch here. This is our little birch area. Birch is really, a little bit warmer. Oof, I'm not very good at this. Smaller, and then look at this. Really like major reductions in birch in the hottest, warmest treatments. And this is worrisome to me in terms of birch, given especially its cultural significance in the region. So one of the things that we have done over the years is our trees like grow out of the treatments. And so we have to replant every 3 or 4 years in the open, every 5 to 6 years in the closed. And that allows us to ask some new questions as we move into these new cohorts. And one of the things that we have done in our most recent iteration of this project is we tend to maintain this core set of species, so we have this long-term record across them. But we have moved into a couple of new areas that I am pretty excited about. I can get my cursor back. And that is, let's erase my drawings. That is fruiting shrubs. I have heard from a number of different people, and some of these have been with some collaborations over at Leech Lake and the Chippewa National Forest, but also working with our Fond du Lac partners of a real interest in fruiting shrubs. As a species that hasn't received a lot of attention around climate change impacts, around management, and a real interest in learning more about these. So in our current iteration, we planted this last spring. We've put in 3 different fruiting shrubs, and we'll be exploring how they respond to our experimental treatments. We put in red-berried elder, elderberry, American plum, and choke cherry. So I'm really excited to kind of see where that angle takes us. And then the second thing that that has come up is interest in seed sources, right? This interest in, well, do we move seed sources? What happens when we move seed sources? And we've dabbled a little bit in that with oaks, and I'm sorry, but we didn't have the data kind of worked up to tell many stories with the oaks. But that paper birch, that species that seemed it had quite some mixed responses, and that is a culturally important species in the region, that just kind of iconic. How many boreal painting scenes do you have out there that have, a birch stand, right? They're just beautiful. And I think that this species into the future needs our care and stewardship. And so and in consultation with the forester at Fond du Lac, uh, picked this as our species to look at seed source variation. And so a colleague collected 14 different populations. So gosh, probably from 20 mother trees at each of those 14 sites, collected seed, and we've been growing these seed up, and we'll be planting them into the worming experiment, to hope to understand more about variation in birch, about southern seed sources of birch. Are they more resilient, especially to those drying treatments? And just thinking about ways that we might put some extra time and care into the species. And I think other species that are suggested to struggle will also, if that is our goal, is keeping those on the landscape, will also need some extra TLC. So 15 years and 45 minutes. Climate change is here. It's happening. It's changed already. I think we know a lot that can inform our actions. People have managed through change in the past, and we can do it now. And I think depending on goals, the approach is going to need to be different for species. Some species, are poised to become more abundant, and that may shift how we think about forests in the regions. But there are other species that are really important culturally, economically, to our region that may need additional creativity and stewardship in the future. So with that, I know this is an hour long, so I like to have time to answer questions, even though I can't see any of you or hear your questions in your own voices. I wanted to give us ample time for a bit of a conversation. So thank you so much for listening. And I'm also happy to connect outside of this webinar with anyone who wants more details or has questions or wants to talk through more things or is interested in collaborating. Yeah, thanks so much.
Great. Well, thanks. And we do have quite a few questions and comments in the chat, so I'm just going to dive right into those. So Matt,
do you want me to take the slides off, or should I leave a?
We can just kind of leave this takeaway, or if you have like a contact slide, if we wanted to kind of pause on that for a moment. But
yeah, I don't.
No worries. Either way, I'll paste that in the chat here. But
Minor details, right?
Yeah. Well, there's only one of you in the Forest Resources Department. I think folks could figure it out. But so Matt mentioned, or from Grand Portage mentioned, we've been observing earlier springs and late winters. Are you modeling these effects? And if not, then how would you extrapolate your findings to the real world?
Great. Yeah. So we are doing some modeling in terms of phenology, um, looking at basically using temperature and real temperature data to model bud burst, leaf coloration, um, and leaf fall in the species. Um, in terms of forest modeling, that is, I am the ecophysiologist and ecologist part of this. And so what I'm hoping is, and what we have been connecting with others outside of our group, is that the data that we are collecting can feed into those forest models that other groups are using. One example that is less regionally specific is that some of our physiology data is being used in these broader vegetation and carbon models. Um, I think it would be really cool, actually, and this question is piquing this in my head, to connect with someone who works with like Landis modeling and try and apply some of these growth and survival, and even some of our uh, uh, the biophysical parts of the work into one of those Landis models. So that's a great idea, one that we haven't done except in more of the not species specific, but forest kind of function specific.
Great, thank you. I wanted to, I think I lost my spot in these comments here. There's a lot. This is awesome. It's great to see folks so engaged, and this is exciting here. Danae asked, why not heat during snow cover? You mentioned not quite just summer, but on the shoulders as well.
Two reasons. The easy one is economics. It's really expensive to heat. And in the winter, if we are moving from -20 to -17, where the plants aren't active in that range of temperatures, then we are spending money to heat in an area where the plants are not going to be responding because they're dormant. So that's the kind of both biological and economic. And then the other piece is, one of the things that happens, as you can see from this figure very clearly, is that the heat lamps melt the snow in kind of patches. And we just felt that this, the winter warming with this infrared approach is not a good mimicking of what winter warming would look like, especially from a hydrological point of view. And so also chose not to warm in winter for that reason.
And kind of on that note, Matt mentioned again that we've observed in our area that we have about the same annual rainfall, but in fewer, heavier rainstorms. How do you think the trees will react to that? Have you seen any of that with your data?
Okay, Lane, can you, I was peeking at some of these. Can
Sure.
you
So
kind
right
of,
under at 934. So Matt, in
oh
their
yeah,
area have about the same annual rainfall, but in fewer, heavier
yeah.
rainstorms.
Yeah, and so yes, Matt, so this is where Um, when we see the aggregated data of increasing moisture in the area, we think, oh, maybe like the future is going to be wetter. And for example, our treatments that are warm but not removing rainfall might be more related to what is happening out in the ground and what might happen in the future. But because of this phenomena, where we have these longer dry periods, I think that the future is going to be a mix of all of our treatments. And because we're going to have these drier periods, there's going to be periods of time where what we're seeing in those dry treatments are the impacts on the plants. And I actually think, and this is like going back to that modeling question that I love, modeling different scenarios of wet and dry over the course of the year could be really interesting, because I feel like a fair amount of this is the balance, right? How much of those dry periods between heavy rainfalls do we have, leading to reductions in physiology that translate into reductions in growth, relative to those like cooler, warmer periods of time. And it's really going to be, if we shift the balance toward the dry, or the impact of those dry is twice as much as the impact of the wet and warm periods, then those dry periods are going to dominate the signal in terms of those juvenile responses, if that makes sense, right? That we're going to be adding up how much wet and how much benefit they're getting from how much dry, and how much negative effects they're getting during those dry periods. And on aggregate, uh, will depends on the aggregate of that variability. Um, if that makes sense to people.
Yeah, and maybe you've sort of touched on this a little bit. We had a question from the Q&A portion, with growth of boreal species going down 20 to 40% and growth of the temperate species going up 20 to 40%. And maybe you've just touched on this here. Is there a net gain, loss, or neutral effect on those overall tons of woody fiber that are grown per acre per year? Is it just going to vary based on composition, or?
I think it will vary based on composition. Um, uh, I'm trying to see. I believe that this, no, this is the proportional is proportional abundances. That's a really good question. We have that. Um, we have that. And my gut feeling, my suspicion based on what I know of the data, is that there's going to be overall more biomass. It's just going to be different species making up that biomass. But don't fully quote me on that. But that's my just thinking about the individual species responses, and our total biomass that we end up harvesting from the worm plots tends to be more. There's more leaf area, which is also partly why the worm treatments actually get more dry down, because there's more leaf area moving water. So yeah, more fiber. It's just going to be different species, I would say. So we're going to have to think about, 50 years from now in our long view, how we adapt to maybe a different mix of species.
And building off that, observation from Christian saying, I think about these longer dry periods sandwiched between heavy rainfall events, and think about earthworms removing the temperature moderating and moisture holding duff layer that may allow some seedlings to endure 2 to 3 weeks without rain versus drying up and dying, and then adding in deer to the mix. So
100%.
yeah,
Yeah. Yeah, I mean, experiments are great for like understanding somewhat controlled conditions. And I mean, this isn't a greenhouse experiment. We're still dealing with out in the world, but there's limits of what we can learn from experiments too. They're like, I think of them as sort of a jumping off point to ask new questions in different contexts.
and I think so. We've got time for maybe just a couple more questions. I don't think I'll be able to get to all of them. Thanks so much, folks. And I believe Eli pasted your email. So if folks have more questions and would like to reach out, make sure you find that comment in the chat there. How might your findings interact with different soil types and landscape positions?
Yeah, we were on both these sites are, well, especially the Cloquet Forestry Center is really sandy soil, so it's kind of on the extreme side of that soil continuum. There's a little more rocky clays at the Ely site, and so we're seeing that site has a slightly more mesic soil, and we're not seeing any differences in our responses among the sites. Um, I think that on richer soils, some of these results might be exacerbated because the species that are really showing strong responses to warming and some resilience are also species that tend to thrive, be more abundant, dominate on richer soils. And so um, those richer sites could favor those species that already are favored. That said, those could become, with stewardship, refugia for some of the species that the future is going to be challenging because they are not such an extreme kind of low soil moisture, low nutrient soil, like the especially the experimental site at Cloquet, if that makes sense. But you would need to probably manage the interactions with some of the species that will have enhanced growth in those sites, if that makes sense.
So we have a couple more questions. I think these are pretty similar here. So from Amanda, just an observation. It's surprising to see white pine doing poorly in this experiment.
Yeah.
It's supposed to be kind of a quote climate winner in other parts of the state. And then Brian mentioned on sandy soils that don't retain moisture very long and regenerating conifers following a harvest. Your data suggests jack pine, white pine, and white spruce may perform poorly long term. So looks like maybe red pine becomes a future conifer of choice. Can you just talk a bit about conifer diversity and what
Yeah.
challenges, opportunities there going forward?
Yeah, I think, Amanda, your comment, that's something that has been like on my mind so much when I see a lot of these climate envelope modeling suggesting, supporting white pine and our results 100% white pine um, uh, across the board is always does poor in the climate change experiments. And I wonder if it's, because it's near some of the edges of its range. I know that white pine's thriving, as I saw another comment on the Anoka sand plain. It's really thriving there. It's warmer there. It's dry. Um, this is one of the mysteries for me. But it's been quite clear across multiple different cohorts, across many different types of years, from wet years to dry years to warmer to cooler years, that um, you know, and maybe it has to do with that being in that mix of species for white pine. I think in the white pine success, and then Oka sandplain tends to be coming into old fields, coming into grassy systems, coming into largely oak dominated systems. Maybe I'm not answering this question very well because I don't know, but I've been curious about it. In terms of conifer diversity, yeah, I think it's going to be a challenge in the future. Um, and it will be something that more care and attention is going to need to be paid if you want to have a diverse conifer mix in the future, because there's going to be additional stressors on those species from dry conditions, from warmer conditions, from neighbors, right? I mean, that's the thing with this, because they're all neighboring each other. And because we have all the herbaceous ferns, other plants there, um, those neighbors, I think, are potentially an important aspect of the responses as well. Um, I would add, we actually have some data on that and somebody that started analyzing the data because for each tree, we know who's around it. And so one of the things that we have a new person working on is, does that matter, right? If you have a white pine with a bunch of other pines, does it grow differently than a white pine with oaks and maples around it? So those neighborhoods. And I think that might give us some new insight into some of these results that might be a little puzzling.
Great. And again, I know we didn't get to all of these questions, but thanks so much, Rebecca, for this really great talk. I've pasted the contact info a couple times here. So the email is rebeccaM@umn.edu. And make sure if you want your CEs, feel free to fill out that Google form, please. And again, oh gosh, even more questions coming in. I'm sorry here, folks. We're a couple after the hour, just to be respectful of everyone's time. We're gonna call it there. But again, thanks so much, Rebecca, for this.
Thanks
And
everyone for being here.
yeah,
I don't know who all was here, but some of the folks I see in the chat are people that I know, and I appreciate you coming, and I'm happy to have further conversations and welcome everyone's ideas because so many of you are out in the woods more than I get to be, sadly, with my other teaching responsibilities and whatnot. And so those of you who are out there in the woods too can really help us think through our data, our stories, and love to hear more from people.
great. Yeah, thanks all, and we'll see you next month on October 14th for our webinar on post-ash silviculture. Thanks again, Rebecca. Take care, folks.